A group of scientists will use the James Webb Space Telescope to search for Earth 2.0 and Jupiter-like exoplanets dispersed around the cosmos. Right after its launch, the James Webb Space Telescope was able to identify indications of the presence of water on an extrasolar planet located about 1,324 light-years away from Earth. This planet, a gas giant named WASP-17b, has an unusually close orbit around its star, making a year on this planet last only 3.7 days. Nicole K. Lewis, an astrophysicist at the Carl Sagan Institute at Cornell University, intends to take advantage of this characteristic to conduct more in-depth research. According to a report from Cornell University, Lewis has been allotted 130 hours of observational time to investigate various types of exoplanets throughout the cosmos. Additionally, she is part of a group that plans to observe specific exoplanets for a total of 200 to 300 hours. These exoplanets range in size from that of Jupiter to that of Earth. Even if her team does not make any significant discoveries within the allotted time, many other teams are waiting for their turn to use the telescope. Teams are selected through the JWST Guaranteed Time Observations (GTO) program run by NASA, which guarantees that the observatory will be used for 16% of its total time during its first 3 cycles of operation. So, how likely is it that the James Webb Space Telescope will find another planet similar to Earth? According to research published by Cornell, Lewis was quoted as saying that by studying different types of planets in various circumstances, scientists can begin to understand why they exist the way they do. This knowledge could help in the search for Earth 2.0. One possible interpretation, according to Lewis, is that the extrasolar planet WASP-17b is one of her favorites. She and her colleagues plan to examine the planet when it passes in front of its host star and measure the emerging light to investigate the planet's chemistry. The spectrograph equipment developed by the James Webb Space Telescope will be used to analyze the light reflected from the planet. These spectra, captured by the telescope, will contain the chemical fingerprints of molecules like water, carbon dioxide, methane, and others. As Lewis noted, they will also look for aerosols, which provide unique signatures of places on the planet, and also at different wavelengths, including clouds and hazes. The Webb telescope is particularly ideal for these kinds of discoveries because it is extraordinarily sensitive to infrared radiation, which, while invisible to the eye, can be detected as heat. Since planets shine brightly in this wavelength, infrared light is considered the best method for studying planetary systems. Lewis further explained why the discovery of Earth 2.0 is so crucial. It would help answer fundamental questions like, how did we get here? Are we alone? And are there any planets in the universe similar to ours? Meanwhile, the Chinese government has plans to search for a second Earth-like planet, not with the James Webb Space Telescope but with their own. Despite multiple high-profile searches, astronomers have yet to find a planet similar to Earth orbiting a star that is analogous to the Sun. In 2026, China plans to launch its own space telescope, specifically to search for Earth 2.0. One of the most remarkable findings in recent astronomical history came from the Kepler Space Telescope, which, after its launch in 2009, monitored 13 million stars until it was turned off in 2018. During this period, Kepler discovered around 2,600 planets orbiting other stars. Some of these planets were found in the habitable zone of their parent stars, though these stars were red dwarfs very different from our Sun. Although exciting, Kepler ultimately failed to find a planet that resembled Earth 2.0 orbiting a Sun-like star, mainly because these stars were louder than expected, requiring extended observation. Additionally, in 2013, 2 of the telescope's 4 reaction wheels malfunctioned, making long-term observations unfeasible. Now, the Chinese government is preparing to launch its own mission in 2026, named Earth 2.0, to search the cosmos for planets similar to Earth that orbit stars like the Sun. About 300 scientists and engineers from over 40 different universities, mostly located in China, are part of this mission. The Chinese team has also come up with a solution to a common problem faced by space observatories: how to cover as large a field of view as possible while minimizing cost and weight. Rather than using a single large telescope, the spacecraft will carry 6 smaller telescopes, each measuring 30 centimeters. These telescopes will work together to observe the same region of the sky that Kepler did with its 1.4-meter mirror. The spacecraft will also carry a seventh telescope to detect microlensing events, where the gravitational field of one star focuses the light of a more distant star, causing the distant star's light to brighten. This sensor will also help detect free-floating planets, shedding light on these peculiar objects. The Earth 2.0 spacecraft is set to be sent to the L2 Lagrange point, a location in space where the gravitational fields of the Earth and Moon are in equilibrium, providing an ideal environment for observatories. The L2 point is already home to several observatories, including the Herschel Space Observatory and the James Webb Space Telescope. During its 4-year mission, Earth 2.0 will orbit L2 and transmit about 169 gigabytes of data every day. The mission's team believes their transit survey will identify around 29,000 new planets, including approximately 4,900 planets similar in size to Earth. Simulations suggest that the expedition should discover between 10 and 20 Earth 2.0 planets by 2030. If successful, the discovery of Earth 2.0 could be one of the most significant events in astronomical history, sparking widespread interest in the composition of these planets' atmospheres and the possibility of water. The next step would be to look for biomarkers like methane, oxygen, and light absorption patterns unique to photosynthesis, which could indicate the presence of life. The final step would be searching for technological fingerprints or technosignatures, such as industrial pollutants like chlorofluorocarbons or even narrowband radio transmissions, suggesting the existence of an advanced civilization. However, Earth 2.0 is not the only mission capable of locating an alternative Earth. Other missions, such as the European Space Agency's Plato mission, set to launch in 2026, also have this potential. But for these missions to succeed, they may need more luck than Earth 2.0. This marks the beginning of a new era in the study of potentially habitable planets, and sets the stage for an exciting international race to uncover another Earth. The question remains, who will be the first to discover Earth 2.0? Will it be the Chinese, the JWST, or is it even possible that another Earth exists somewhere? The search for Earth 2.0 has become one of the most significant quests in modern astronomy, driven by the desire to find a planet that shares similar characteristics with our own, particularly one that could potentially support life. While astronomers have been searching for exoplanets for decades, only in recent years have technological advancements allowed for more in-depth exploration. Telescopes like the Kepler Space Telescope, the James Webb Space Telescope, JWST, and now China's Earth 2.0 mission are pivotal in uncovering the mysteries of distant exoplanets. The Kepler Space Telescope, launched by NASA in 2009, made some of the most important discoveries in the search for Earth-like planets. It monitored over 13 million stars, detecting tiny dips in light when planets passed in front of them, a method known as the transit method. By 2018, when Kepler's mission ended, it had identified over 2,600 exoplanets. Among these were planets located in the so-called habitable zone of their stars, a region where conditions might allow liquid water to exist on the planet's surface. While many of these planets were intriguing, they were often found around red dwarf stars, which differ significantly from our Sun. The discovery of potentially habitable planets orbiting red dwarfs sparked excitement, but astronomers realized that they would need more advanced technology to refine their search for planets like Earth that orbit stars similar to the Sun. The James Webb Space Telescope, which launched in December 2021, has revolutionized our ability to study exoplanets. Unlike Kepler, which primarily used visible and infrared light to detect exoplanets, the JWST is designed to observe the universe in infrared wavelengths. This is significant because many of the chemical signatures of potential biosignatures, such as water vapor, methane, and carbon dioxide, are best detected in the infrared. By studying the atmospheres of exoplanets in this wavelength, JWST can gather crucial information about a planet's composition and whether it could support life. One of the most promising features of JWST is its ability to perform spectroscopic analysis on the light that passes through an exoplanet's atmosphere when it transits in front of its host star. This allows scientists to measure the chemical composition of the planet's atmosphere, looking for specific molecules that could indicate habitability. For example, the detection of water vapor and oxygen could suggest that a planet has the necessary conditions for life. The discovery of methane, in particular, has been noted as a potential biosignature, as it is often associated with biological processes here on Earth. Despite these advancements, the discovery of an Earth-like planet has proven to be extraordinarily challenging. While astronomers have found many planets that could potentially support life, none have met all the criteria for being considered truly Earth-like. These criteria include a planet's size, its distance from its star, in the habitable zone, and its atmospheric composition. In addition, many of the planets discovered by telescopes like Kepler and JWST are gas giants, much like Jupiter or Neptune, which are not suitable for life as we know it. This is where China's upcoming Earth 2.0 mission comes into play. Set to launch in 2026, the Earth 2.0 mission will aim to address some of the challenges faced by previous missions. Unlike Kepler, which relied on a single large telescope, the Earth 2.0 mission will utilize 6 smaller telescopes, each 30 centimeters in diameter, which will work together to observe the same region of the sky. This innovative approach is expected to provide a wider field of view while keeping costs and spacecraft weight to a minimum. The goal is to identify exoplanets that are similar in size to Earth and orbit stars similar to the Sun, a task that has proven difficult for other telescopes. The Earth 2.0 spacecraft will be placed in a halo orbit around the L2 Lagrange point, a location in space where the gravitational forces of the Earth and the Moon are in equilibrium. This position allows for a stable observational environment, free from interference from Earth-based signals and radiation. From this vantage point, the spacecraft will conduct its search for Earth-like planets over the course of a 4-year mission, transmitting an enormous amount of data back to Earth each day. In simulations, the team behind the Earth 2.0 mission has predicted that it could identify around 29,000 new planets, with about 4,900 of them being roughly the size of Earth. This represents a significant leap forward in our search for a planet that might be able to support life. The mission will use the transit method to identify planets, looking for the small but detectable dimming of a star's light when a planet passes in front of it. By measuring the size of the planet and the time it takes to complete its orbit, scientists can determine whether it is located in the habitable zone of its star. In addition, the Earth 2.0 spacecraft will be equipped with a 7th telescope designed to detect microlensing events. These events occur when the gravitational field of one star focuses the light of a more distant star, causing a brief, temporary increase in brightness. By studying these events, scientists can infer the presence of planets around the stars involved. The success of the Earth 2.0 mission has the potential to be groundbreaking. If it successfully identifies Earth-like planets, it will open new avenues of research into the possibility of life beyond our solar system. Discovering planets that are similar in size to Earth and orbit stars like our Sun would provide a wealth of information about the types of environments that could support life. In the future, astronomers may even be able to study the atmospheres of these planets in greater detail, searching for biosignatures that could indicate the presence of life. This search for life on other planets is not just limited to detecting the right conditions for life. Scientists are also looking for technological signatures that could suggest the presence of advanced civilizations. These technosignatures could include pollutants in the atmosphere, such as chlorofluorocarbons, CFCs, or even radio signals that are intentionally transmitted by intelligent beings. While this area of research is still in its early stages, the discovery of such technosignatures would be a monumental event in human history, confirming that we are not alone in the universe. The search for Earth 2.0, whether through the James Webb Space Telescope, the Earth 2.0 mission, or other future missions, marks the beginning of a new era in the study of exoplanets and the potential for life beyond our planet. As technology continues to advance, astronomers are gaining the tools they need to search the cosmos more effectively and in greater detail. While the discovery of another Earth-like planet is still a distant goal, each new breakthrough brings us closer to answering some of the most profound questions about our place in the universe. The hunt for Earth 2.0 is not just a scientific endeavor but also a philosophical one. It challenges us to think about our place in the cosmos and whether life elsewhere is possible. As our understanding of the universe expands, we must consider the implications of discovering other Earth-like planets. Could these planets harbor life? If so, what would that mean for our understanding of biology, evolution, and the potential for interstellar communication? The answers to these questions will shape the future of space exploration and our understanding of life beyond Earth. In conclusion, the search for Earth 2.0 is one of the most exciting and ambitious scientific endeavors of our time. With the help of advanced telescopes like JWST and the upcoming Earth 2.0 mission, astronomers are on the cusp of making discoveries that could change the course of human history. While the discovery of another Earth-like planet is still a long way off, the journey to find it promises to be one of the most thrilling adventures in the history of science.